Hey, Dr. B here, and let's take a look at rate law. Now, you might think that this is the study of the effect of temperature on rate, but no, it's actually just the effect of concentration on rate. That's not necessarily the first go-to method for increasing the rate of the reaction, but it gives nice, clean results. Three outcomes are likely. You double the rate of a reactant, you double the concentration of a reactant, it has no effect at all. You increase the concentration of a reactant, it has a proportional effect. For example, triple the concentration of reactant A and the rate triples. Or if you're lucky, you might get an exponential effect. We double the concentration of a reactant and the rate of the reaction quadruples, 2 squared, or perhaps increases 8 times 2 to the third. Let's take a look at this for this reaction here. We're decomposing nitrogen dioxide into nitrogen monoxide and oxygen. We've got some coefficients. Everything's in the gaseous form. Let's have a look. The generic setup is that the rate will be equal to some constant K times the concentration of the reactants to some power that has to be determined experimentally. So K we call the rate constant. A small number means a slower rate, a high number means a faster rate, and is the reactant order that we referred to up here. If we had no effect, n is 0, and in fact the rate would just be equal to k, since anything to the 0th power is 1. If it's proportional, we put a 1 there. If it's exponential, it might be a 2, a 3, etc. Some common errors. Students assume that you can determine what n is without doing any experiments at all. No, you have to do rate law experiments to figure out what's the deal. 2, we assume these numbers here, these coefficients, become the exponents. They do not. This might be more of a problem after you've studied equilibrium, where they do. But for rates, the reactant order has to be determined by experiment. And 3, people start putting concentrations of products in the denominator, things like that. No, for rate law, it's simply equal to a rate constant times the concentration of the reactants to some experimentally determined rate, reactant order, and that's it. So let's apply this to this reaction shown here generically. We got monstrous coefficients here. We got lots of products, but we can simplify it. It will simply be equal to some constant K times the concentration of A times the concentration of B, and we'll put up some letters for those exponents that we do not know yet. They have to be determined by experiment. So it's much simpler than it looks there. We can also say the overall reaction order will be just the sum of those exponents here. So if it is, follow the lingo, first order with respect to A and second order with respect to B, for example, we'd simply say that it's third order overall. So you just add those exponents to get the overall reaction order. That's a quick introduction to rate law.